Hey everybody, Dr. B here. We're turning a corner here, going from descriptive statistics to inferential. And we're also turning a corner in going from talking recently about individuals to talking about groups of individuals, talking about samples, and doing research with samples to help us understand populations. So in the previous block of material that we covered, we were talking about normal distributions. We learned a lot about them. And we also learned about z-scores, and we learned how z-scores are a tool for taking us forward about an individual score, like an IQ score, something that we in a population that we know is normally distributed. We know that intelligence is normally distributed like this. Z-scores are a tool for helping us go forward from a known score, like say an IQ score of 113, forward to answering questions about percentiles. Okay, so we could work that forward through the z-score formula and use a z-score table to answer a question about what percentile would an IQ score of 113 be. We also learned that we can do this backward if we know the percentile. We could say, well, what would be a 98th percentile IQ score? And using those same tools and different versions of the formula, we can work backward to figure out what score is the 98th percentile. Well, we're no longer interested in talking about individuals, okay? We aren't typically interested in psychology with individuals unless we're counselors or clinicians. When we do research, we typically don't do case studies with individuals. We use samples to help us understand things about populations. Whether it's surveys, using a sample to, survey a population when we don't have access to the population, or when we are experimentalists conducting experiments, we'll use samples to give treatments to. We'll take a sample and subdivide them, say in the simplest case, into a control group and an experimental group, and we'll administer some treatment. Maybe we'll give a smart pill to see if it affects intelligence instead of just measuring intelligence. So one group of kids is going to get a placebo, another group's going to get something that you've speculated or hypothesized is a treatment to increase intelligence. And at the end of the day, you want to see if that group of kids who took the treatment, the actual treatment, have a different IQ score, preferably a better, higher IQ score than the control group that got the placebo and that should not have changed their intelligence. Well, we need tools to understand and answer questions like, is that sample that got the treatment significantly better? Is it different? Is it rare? Is what I saw rare? And we have talked about rare and how these tails of a distribution contain what we call the rare areas. Okay, scores that are so low as to be considered rare, and scores that are so high as to be considered rare, and everything in between we called, in this normal curve, we called normal. All right, if you're in the normal range of a normal curve, that's not unusual. But gee, if you have an IQ score way up here, it's considered rare, and something maybe is unusual. Now, in the context of doing an experiment, if not just one person wound up being up here, with increased intelligence, because if we just gave a smart pill to one person and they had a high IQ, that even if you knew what their IQ was before and it was in the normal range, and now the individual has a high IQ, well, hey, that's one person. This stuff seemed to have worked on one person, but maybe there's expectations, maybe something else went on, maybe they matured, maybe I misfired on the first measure, or maybe this test afterwards is kind of a anomaly. All right, so anyway, in your gut you can understand that you don't really trust one person or even a small handful of people. So we typically go and get samples, all right? So our attention now is focusing not on the individual scores, but on how a collection of people do, a collection of people in an experimental group, and how they compared with a collection of people in the control and placebo group. The two tools that help us, the two theories and concepts that are going to help us answer those kinds of inferential questions about samples are sampling distributions, which I'll talk about in this episode, and next time I'll talk about Central Limit Theorem. So hand in hand, the concepts of sampling distributions and the Central Limit Theorem help us to be able to answer these kinds of probabilistic questions like, is this rare, this result that I see in this group or groups, okay? These treated groups, are they are they rare? Are they significantly different than the groups that did not get the same treatment or different kinds of treatments? Okay, so sampling distributions. So what are they? Well, you're now familiar so far with what are called frequency distributions. Frequency distributions is shorthand for a frequency distribution of raw scores or a frequency distribution of individual scores. Okay, so those were telling you how frequent something is in a population. So we were, of course, referring to frequency over on the y-axis, and the scores were, you know, down here. Okay, or whatever independent variable we were referring to. Okay, so that was those were frequency distributions of individual scores. Well, what's a sampling distribution? A sampling distribution looks, as you're going to see, it looks like often like a frequency distribution. Okay, in fact, as we're going to see in the next episode about central limit theorem, the central limit theorem tells us that under very likely situations that we're going to be using in research, we will see sampling distributions that are normally shaped, just like the frequency distributions that we were talking about for some things like intelligence. Okay, so they do have some similarities. The axes are the same, whatever the shape winds up being. Okay, so we report frequency of something, but down here it's no longer going to be, you know, raw scores or individual scores. It's going to be means. The most likely sampling distribution that we're going to refer to are going to be the means for samples down here, okay, instead of raw scores for individuals. So there's one more thing that we need to know anytime we're working with a sampling distribution, is the sample size that we're referring to. Okay, let's make more sense of this with an actual example here. Okay, so I might be interested in knowing how many hours you all spend studying, and, you know, in class and studying. Now, I might want to know that for you as an individual. Fine, great, and I could do that. But I have a more specific question. I am interested in my subset of students, my subset of, you know, psych stat students. Okay, how much time do psych stats students in particular spend studying? So that's my subset of the population that I'm interested in, and it's also going to be my subset that I can use for sampling to answer this question. Okay, now I could run around asking individuals, but I'm going to do it in a more organized way. Okay, I'm going to do it class by class. Okay, I'm going to be very patient, and this is going to be a study going on for years and years and decades of teaching psych stats classes. Okay, now in a typical psych, let's just pretend that the maximum capacity for this class is 20 students. Okay, so let's just make a pretend assumption that it's supposed to be 20 and it always is 20. Okay, it isn't always 20. Sometimes it's less, sometimes it's more, but let's just pretend that it's always 20. So the samples that I'm going to use are always going to be 20 students at a time. I ask the 20 students in the class each semester to report typical amount that they study. Okay, so I get the values from 20 people at a time. Let's do this one at a time. So I ask the first group of 20 students how much time they spend doing coursework per week. And let's say that I get from this first group some number like 18. I'll just put that there just kind of arbitrarily. 18 hours. All right? So that box represents that first group of 20 people giving me a mean of 18 hours. Now, some studied way less than that, and some in the group studied way more than that. You get the idea of a mean, right? So this is the mean for 20 people, and it happens to be 18. Okay? Now, so far I have one entry into what's going to become a sampling distribution. So far it's not really a distribution, it's just a block. That block is just the one group so far. All right? So the next section I get, let's say I'm teaching several of these sections a semester, so I can ask the other class how many, those 20 people to give me their number, and I calculate their mean. So the mean of that group, and that group kind of similarly, let's say, had a mean of 19 hours that they spend studying for all of their classes, spend time in and studying for classes, okay? So now I have two entries into my budding sampling distribution. So hopefully you kind of get the idea here. So the third group, to put some more numbers in here, oops, 16, 15, 14, 13, 20, 21, 12, okay, and I could go down and up in other directions here. I get another group and they spend 16 hours, and the fourth group was a really hard-working group that studied, they did 21 hours worth of combined schoolwork. 17 for the fifth, and another group had. Now look what happened here. Okay, a second group came along, so I put their block on top of the other one. Okay, so remember over on the y-axis here, we're recording frequency. So 1, 2, 3, 4, 5, 6, 7, 8, and so on. All right, so far I got, two groups that studied 16 hours. And so I continue, all right? And oops, group that doesn't do so much work. Once, that class has got a mean only of 12 hours. And here comes one of 50. Group that studied 24 hours over here, and 17, and then 13, and another one of 16, and then I had a group that studied 14, and then I had a group who studied 18, and one group that studied only 11, and anyway, so I've got 10 or 12 or something sections that I'm pretending that I've sampled here so far, okay? So you can see I'm starting to collect samples. So a sampling distribution is going to be just that. It's going to represent the samples that I could get, or sometimes it's referred to in a more theoretical sense. So now let's just imagine that we did this and we did this and we did this and we did it, and imagine that we got it for theoretically the whole population of samples that I could get, okay? And that would be some huge number, all right? Too huge for any one person to collect in a lifetime or anything like that, okay? So now imagine this being filled up with thousands and thousands of blocks, perhaps, okay? No one has the time or energy to get all thousands and thousands of them, all right? But it theoretically exists. All of the possible samples that I could, all the sample means that I could theoretically get, okay? All in a pile. So how that pile is shaped is its sampling distribution. So sampling distributions are sometimes just like a frequency distribution was kind of shorthand for frequency distribution of individual scores. Sampling distributions is a short way to say sampling distributions of sample means. Or even sampling distribution of all possible sample means, okay? So each one of these blocks is no longer a person. It represents a group of 20 people and how they did as a mean, okay? Now, the distribution of all of these means is itself going to have some parameters, just like the frequency, the raw score frequency distribution would, if we weren't talking about samples of 20 students at a time, but just all students in the pile, okay, individuals, the pile of individual students, okay, how much time do all students spend studying, okay, as individuals? There would be some theoretical population parameters for them. There would be a population mean, and there would be a population standard deviation. Well, likewise, this sampling distribution is going to have a mean. We'll call that a mean of means, all right? So some new parameters here. A sampling distribution is going to have a mean of all those means, okay? So I like that little symbol here. So that's a mu, that's not an m, all right? So theoretical, right? When we're talking about populations, we use Greek symbols here. And so when we were talking about raw scores, mu all by itself represented the mean, okay? Well, the sampling distribution is now made up of means, so I like this elegant symbol that we use, the mean of means. X bar is sample means. All these blocks down here are X bars, right? Each one of these was an X bar. Okay, I'm not going to fill them all in here, okay? All of those were means, and so there's a theoretical population mean of all of those means. Next time I'll go into more detail about this, but in the central limit theorem we'll beat home this concept a little bit more here and put these things together. And we're going to find out there in more detail that the mean of means is very, not coincidentally, always going to be equal to whatever the raw score population mean is. Okay, so that's neat. Okay, well, if we can get a mean for this distribution of means, we can also theoretically get the standard deviation of all of these means. And so to be consistent, we'll refer to it this way. So, but now we're not going to be consistent. Okay, so it looks like we should call this the standard deviation of the means. That's what I would call it if I was naming things. That symbol, you know, the mean of means and the standard deviation of the means. Okay. Well, we have a new term for this, and I'm going to put it in shorthand here. That symbol is called the standard error of the means, sometimes just called the standard error, all right? Sometimes just called SE, all right? This sampling distribution is going to have its population parameters. It's going to have a mean of means, and that mean of means will always equal the raw score population mean value, as we'll see next time. This distribution will also have a standard deviation. I'd like to call it the standard deviation of the sample means, but the gods that be called this the standard error. And next time we'll learn a little bit more about how and why that thing is not equal to this. All right? It does not equal the population standard deviation. It equals something kind of related to it, okay? It's equal to the population standard deviation divided by the square root of whatever sample size we use, okay? So that's a goofy thing, and we'll talk more about that when we talk about central limit theorem. So there we have it. You now know the concept of a sampling distribution. The one I'm drawing here is only begun. It would have to be fleshed out, and in real life we would continue to add blocks to it, and we might see some other ones, and okay, and it would start to pile up here, and these are just kind of random boxes I'm putting in, and it would start to build, and we will see in the next episode on the central limit theorem the neat way that these things tend to stack up, okay? We'll learn there as a preview that if the sample size is big enough, and 20 is big enough, the resulting distribution of all of these blocks will wind up being in kind of a normal distribution. That's what we'll see in the central limit theorem next, okay? So I hope that's clear now, this concept of a sampling distribution. I want you to know how they're related to frequency distributions. Frequency distributions of raw scores versus sampling distributions of sample means. I want you to be able to compare and contrast them. How are they similar? How are they different? They're similar in that they display the same thing. They're displaying how frequent something occurs. In the first case, how frequent a score occurs. In the second sampling distribution case, how frequent these means occur. Okay? They might be normally distributed, as we'll see in the central limit theorem discussion. Okay, they might not be. In the population, we used examples like intelligence. We stuck to examples that were normally distributed, but remember, not all variables are normally distributed by the individuals. Okay, not all data is normally distributed. Some things may be skewed or rectangular even, or other different weird shapes. When we were doing z-score stuff, we were limited to individual scores of variables that are normally distributed. As we're going to see next, when we do sample research, thanks to the sampling distributions and the central limit theorem, we can use any variable. All right, that's for next time. So, hope this made a little bit of sense. Sorry for the sloppy drawing and writing. My magic pad. See you next time.